So now that we've gone through every single digital logic component in excruciating detail, it's now finally time to put it all together and explore the topic that this playlist was put together for: a computer. More specifically, what are the basic fundamentals of a computer architecture? What's required to be a general purpose computer? And how can we piece together the components we've been learning about to build one? What I will not be covering is how to build one specific computer in any specific medium. I'll leave that sort of thing up to you as an exercise to test yourself and see how well you do. So, first things first, let's talk formal definitions. What is a computer and what does it do? Well, for some of you, your first thought is a computer is that big box in the corner of your desk connected to a monitor, keyboard, and mouse. Or it's a laptop or a tablet or a smartphone. And while these are indeed computers, they are a subcategory of computers called personal computers. In fact, the broader category of computers can exist anywhere in any form, from cars to kitchen and household appliances to traffic light controllers and more. What they all have in common, though, is that they all on some level perform calculations. That's all a computer is. It's a machine that performs calculations. In fact, prior to the early 20th century, it didn't even apply to machines. The word computer was a title given to mathematicians who were hired to perform calculations for various purposes. It wasn't until the early 20th century, when machines started to take over that field, that the meaning of the word shifted. So how does a machine perform calculations? Well, we already saw an example back in the abstractions video, where I provided a sample circuit that could solve the quadratic formula. But how can we turn an equation like that into a circuit? Well, remember that every equation is comprised of several simple operations that can be daisy-chained together to produce a final result. These simple operations can then be implemented using the components we've already learned about and then wired together to get the same behavior. While these sorts of circuits can perform calculations, they are only able to perform one kind of calculation. They are application specific, only able to perform a sequence of operations of this length and of this order. If we want the circuit to be general purpose, then we need to be able to calculate any equation, running sequences of operations that are of any length and of any order. Let's start by addressing the length aspect. Suppose we had a sequence of 5 numbers that we wish to add together. If we just use a chain of adders, it would get the job done, and we could sum sequences of numbers up to 5 in length, since any unused inputs can just be set to 0. But what if we wanted to sum numbers in 6 of length, or 10 of length, or 100, or 1,000? We would need longer and longer chains to handle these situations. And since we can always add one more number to the sequence, we'll never have a circuit that can truly handle any length. To fix this, instead of spanning our circuit across space, we can span it across time instead. Using just a single adder, we can tell it to add the first 2 numbers together, then add the third number to the total, then the fourth, and so on, so long as we have numbers to add. Now, since we're dealing with time, that means we're dealing with state, which means we need registers to implement this sort of circuit. So, simply by adding a register to one of the inputs, we create a sort of accumulator that can hold the intermediary answers while the circuit is calculating. We can clock this register every time we want to add a new number, and just provide that number manually. But another option is to place those numbers we want to add into a ROM. Provide an address to the ROM using a counter circuit, and we can partially automate the process by first latching the accumulator, then incrementing the counter. We can then fully automate this process by connecting both of these update lines to a clock. With this, we have a way to sum up any arbitrary length of numbers without needing to modify the circuit. Perfect if we just want to sum things, but what about performing other operations? Well, if we replace the adder circuit with an ALU, and then add some function select information to the ROM, we can not only perform sequences of any length, but of any order of operations as well. To show this, we can take the equation from earlier in the video and convert it into operations in the ROM. Just like before, we start by identifying the daisy chain of operations that are used to calculate the equation. But this time, instead of equating each operation to a circuit, we equate them to a value operation pair. The values, of course, will be replaced by their actual numeric values, but the operations? What do we do with that? Well, recall that the function of an ALU is controlled by groups of wires. Granted, each wire controls a small behavioral aspect of the ALU, but all of these wires together describe the overall behavior. What's more, all of those wires can be thought of as a single integer, meaning every function of the ALU can be mapped to a unique number. Replacing every operation in our sequence with the corresponding number gives us a sequence that can be loaded into the ROM. This sequence, by the way, is what's referred to as a program, and by loading that program into our basic computer, we've effectively programmed it to calculate our equation. Now, that makes for a very simple but still very versatile computer. But the only big question now is, what function should the ALU have? You could have an ALU with all sorts of fancy functions. It doesn't really matter all too much, but the bigger the ALU and the more functions you have, the larger the circuit is as a result, and this could possibly slow down your computer. Alternatively, you can strip it all the way to the basics and have an ALU that only subtracts. You can actually perform any computational operation using just sequences of subtraction operations. It's very simple and very fast, but the result would be a very large and complex program. Like all things, it requires striking a balance. Where that balance point is up to you, but most computers typically have the following functions. They're versatile enough that you can calculate almost anything with relative ease, but also simple enough that the hardware remains simple and compact. Now, this sort of circuit gives us a very basic computer, and there's a lot that it can calculate, but there are a few limitations. One limitation is the fact that for any binary operation, one of the operators must be a constant. This works if you have an operation tree that looks like this, but what about one that looks like this, where one operation gets both of its operators from other operations? In this situation, the output of one operation has to be set aside while the other operation gets executed. Once both results have been figured out, then they can both be operated on to continue execution. To set these intermediary results aside, we need another register to act as a second accumulator. When using this configuration, we can use one register as our accumulator, like we already did, but once we get to a point where we need to solve another branch to move on, we switch to the other register and start using that as an accumulator. Of course, at some point, we need to use both registers in an operation, so we need to give each register the option to use either input of the ALU. So how do we modify our basic computer model to include a second register? Well, first we add the other register, and at this point we'll just connect it to the same buses that the first register is connected to. Of course, if we clock both registers at the same time, we'll just be saving 2 copies of the ALU's output. So we need a way of selecting which register gets updated. This will require a controlled buffer or an AND gate, and those will have to have a corresponding connection to the ROM. Likewise, we don't want each register outputting to the ALU at the same time, so a read line will need to be connected between the registers and the ROM. We already saw that these registers will need the option to use either inputs for the ALU, so giving the registers a second read line will be needed. And those will need connections to the ROM as well. And with that done, we now have a second register at our disposal. Using this computer is much the same as it was before. We can provide a number and a function to perform an operation, but we also need to specify which register we're getting the other operator from, as well as where the result is going to go. We can also just perform an operation between 2 registers by reading from the A bus on one and the B bus on the other. This won't conflict with any data coming from the ROM, so long as the number provided by the ROM is 0. You can of course add more registers. In fact, you can have as many as you like. Keep in mind though that the number of control lines you will need will grow with every register you add. Now, there are ways of reducing the number of control lines, though. For example, if you assign one register to always be the source or destination of any copy operation, that's an operation where data is simply copied from one register to another, then all you have to do is provide a read and write line for all the remaining registers. You could even bundle them using a decoder. This simple architecture shows how everything moves through register 0, and that operations only happen with registers 1 and 2. This sort of computer architecture is advantageous for its simplicity, but performing any meaningful operation will require shuffling registers around. So again, you have a trade-off of hardware and software complexity. Similar to the problem of sequencing adders, if you give your computer a certain number of registers, you're almost guaranteed to eventually encounter a program that will exceed the number of registers that you have. Now, since you can't add an infinite number of registers, the next best thing to do is to add RAM. Doing so is pretty simple. A read and write line can be connected to your ROM, and the address for the RAM can be provided by the ROM's data output. You just need an extra signal to control whether the data is sent to the data bus or to the RAM's address bus. If you want to save a register, simply read from the register. Direct the ROM's data to the RAM's address, provide the address, and select the write line on the RAM. Select read on the RAM and write to a register to restore data from RAM. Of course, providing an address directly is one option, but another option is to have a register provide the address itself. In this sort of configuration, this register is referred to as a pointer register because it points to a specific location in memory. This sort of configuration seems useless at first. After all, it requires more control lines from your ROM, and accessing memory would take two operations if it's done this way, one for loading the address into the pointer register, and one for accessing memory. But saving the address in the register can be advantageous if you have to use that address repeatedly. There's also other uses when it comes to loops, but we'll be covering that later. Now, a computer that solves these equations with a fixed value is useful, but what if we want to change the values? We'd have to stop the computer and modify the program. But what if we wanted the computer to run the program and ask us for the inputs at runtime? How about displaying the results? What if instead of looking at the register or memory contents to get our answer, we had the computer push the answer to a printer or a display? Well, what we need is for the computer to communicate with the outside world, and we can do that through input-output ports, or I/O ports for short. I/O ports are pretty simple. In fact, they work just like RAM. An address is provided, along with a read or write signal, and data is transferred between an I/O port and a register, or a register and an I/O port. In fact, the only difference between RAM and I/O is where the data is going. In RAM, the data gets stored in another register, and simply sits there until it's needed again. In I/O, though, the data is still written to a register, but there's another circuit called an I/O device on the other side of that register, waiting to use that register's content. In a sense, I/O is just a register that two circuits use to share a communication channel. If you're wondering what can be used as an I/O device, the answer is all kinds of things. You can make I/O devices that simply act as connections to the outside world, such as keyboards and monitors, or you can connect it to a robot that takes commands in the form of an integer. Or you can connect it to another computer to act as a coprocessor, handling specific computational jobs that the main processor may be too slow to handle. There's no limit to what you can use as an I/O device, but the general rule of thumb is if you need something to communicate with your computer, it's done through an I/O port. So our basic computer has a lot of nice features now, and can calculate a lot of different things, but it can't calculate everything. For that, we need to introduce a few new concepts, namely branching, jumping, and calling. Let's start with jumping. Suppose I have an I/O device that will always produce a new number every time I read from it, and I want to sum up these numbers indefinitely. In my program, I can have an instruction that loads the first number into the accumulator, then adds the next number, but then what? If I want to add more numbers, I need to keep repeating this code that imports and sums the next number indefinitely. Even if we have a program ROM that was infinitely long, we don't have the time to repeatedly write this code an infinite number of times. So instead, what I'm going to do is break the linearity our program has had up until now, and introduce an instruction that forces the program to jump to a different instruction. This instruction, appropriately enough, is named the jump instruction, and when the program encounters this instruction, instead of progressing to the next instruction, it progresses to the instruction pointed to by the data field. In this example, instruction 0 loads a number from I/O and saves it to the accumulator. Instruction 1 loads another number from I/O into a different register, and instruction 2 adds these two numbers together and stores the results in the accumulator. And instruction 3 jumps back to instruction 1. Once the computer is back in instruction 1, it loads another digit from I/O, adds it, and then jumps back again. This program, while only being 4 instructions long, can perform summations for eternity. So how do we implement this instruction? Well, it's actually pretty simple. By replacing the up counter going to the ROM with a counter register, we give ourselves the option to overwrite the counter's content at any time with anything. We just need to add another control line telling the counter register when to increment and when to jump. Going back to the subject of RAM, I mentioned that pointer registers can be useful in loops. Well, suppose we had an equation and we wanted to apply it not to a single integer, but to a whole list of integers. We can set up a pointer register to point to the beginning of the list, perform the operation with that data, and then increment the pointer before jumping back to the beginning. Doing this repeats the code with a different input value, and letting this run applies our equation to all values in memory. Now with a jump instruction, that allows us to repeat a segment of code indefinitely. But what if we only want to repeat a segment of code a finite number of times? Well, that's what a branch instruction is for. The branch instruction behaves just like a jump instruction so long as some condition is met. If the condition is not met, however, then execution proceeds linearly as normal. Now, what's the condition that must be met? Well, much like the function of an ALU or the number of registers you have in a computer, it's entirely up to you. But most computers will include conditions like register equal to 0, register does not equal to 0, register is less than another register, greater than or equal to another register. If you haven't pieced it together, it's basically the output of a digital comparator. Now this is fortunate for us because, as we discussed in the ALU video, ALUs typically already have comparators built in, and we can access that information using the ALU's flag outputs. We just need to modify our circuit a little bit to utilize them. So, first we add a branch control to our ROM, connected to our counter register through an AND gate. When this is enabled, and our selection condition is true, the counter register will jump like it received a jump signal. However, if the selected condition is not true, the counter register will count like normal. Now, we just need to create a circuit that can generate this condition past a signal. First, we want to create a circuit that can select one of our ALU flags. You can create a circuit that selects more than one flag at a time, but most computers will typically only select one flag at a time. Next, it's best to add an XOR to the line. The reason for this is it allows you to check for the opposite condition as well. For example, if you wanted to check that a register did not equal 0, we can just check the equals 0 flag and invert the result. If the flag does not equal 0, the equals 0 flag will be off, and the XOR gate will invert it, making it on. By the way, this also works as a nice cheat to get greater than or equal to flags if you only have a less than flag, and likewise with a less than or equal to flag if you only have a greater flag. And that's pretty much all we need. We can take that XOR output and pass it as our condition pass signal, and now our computer supports branching. Now, to branch, all we need to do is send a register or two to the ALU, select the flag that we want to read, enable the branch signal, and send the branch to address to the counter register. Now that we have the circuit figured out, let's see how the branch instruction is actually used. Let's say we want to execute a block of code 5 times. What we can do is load the number 5 into a register, then run our code. Then we can decrement the register, and check to see if it's not 0. If it is 0, we jump back to the beginning of the block of code and repeat. This will repeat again with the count register equal to 4, then 3, then 2, and then 1, until finally it's equal to 0 and the condition fails. The end result is the execution continues past this block of code only after it is executed 5 times. Now, I mentioned that you can use flags to control branch instructions, but now the question is what kind of flag should you include? I mentioned in the ALU video that there are all kinds of flags that you can have. Well, what are the most common ones that computers tend to have, and what are they for? Well, on top of the standard ones like equal to, less than, or greater than, you can also have flags like the carry flag, which can be used to indicate if an integer overflow occurs. You can have a parity flag, which is used to indicate the parity of an integer. You can have a half carry flag, which indicates a carry between bits 3 and 4 in a byte. That one is actually very useful in binary to BCD instructions, by the way. You can also have an overflow flag, which is like the carry flag, but it takes the input's integer sign into consideration. There are other flags you can include as well, but those ones will usually cover most conditions you would want to concern yourself with. Which ones you want to add, though, is up to you. One last tidbit of information I want to share about flags, though. As it stands right now, the flags are sampled directly from the ALU as it's evaluating the contents of registers. This means that the register evaluation and branching all happens in one instruction, but you don't have to do it this way. You can store the flags in something called a flag register, then branch based on the status of that register in a separate instruction. But why would you want to do that? Well, storing something like the carry flag allows you to use the carry bit in an add plus carry instruction, which allows you to add integers wider than your register width together. But it also allows you to store the flag's current state and restore it later should you need to. That sort of thing really is only useful if you're implementing interrupt handling and or giving your CPU a protected mode, which is outside of the scope of this video. Now that our computer is able to perform jumps and branches, we have everything we need to be a true general-purpose computer. Meaning, if we build a computer that did just these things, we could calculate anything. That said, though, there is one more concept that I want to cover, because it makes reusing your code a lot easier, and that is the idea of a subroutine. And to understand what a subroutine is, let's imagine we have a program, and that program has segments of code that repeats multiple times. We can shrink the size of our program and make the process of writing it a lot easier if we extract out the repeating code, and then just jump to it anytime we needed it. This is the basic idea of a subroutine, and while you might think our computer can handle it as it is, there is a catch. If we jump to our subroutine and then execute it, where is the program supposed to go to from there? If you think it should go back to the code just after the jump instruction, you'd be correct. But what happens when we jump from elsewhere in the program? Well, when the subroutine ends, it's just going to jump to just after the first jump instruction. What we need to do is save the address of the next instruction, pass that to the subroutine, and then tell the subroutine to jump there when it's done. This act of saving the address before jumping is called a call instruction, and is what we use to enter a subroutine. And the act of jumping to a saved address is called a return instruction, and is what we use to exit a subroutine. So how do we get our computer to call and return like that? Well, if we give our computer the ability to read the contents of the counter register, we can copy its content to another register. And since we need that address to point to the instruction after the call instruction, we need to increment its value by 1. Then, once that's done, we can jump as normal to our subroutine. This register now contains the return address for when we're done executing that subroutine. So long as that register remains safe, we can return to where we left off once the subroutine is done. And we can do that by simply taking the saved address and putting it back into the counter register. Nothing too complicated, at least not yet anyway. I say that because there is another catch. Suppose you write a subroutine that calls yet another subroutine. If you follow the same steps as before, you will overwrite your return address with the new return address. The new return address will allow you to return to the first subroutine, but now that subroutine's return address is lost. We could change the properties of the call instruction and have it save the new return address to a different register, but that only works if you know ahead of time what registers you will have to use. If you don't have that information, you risk overwriting a return address. So what can we do instead? Well, what we need to do is store one address, then store a second address, then a third address, and then when we want to return, retrieve the third address, then the second address, and then the first address. What we need is a first-in, last-out storage solution. Sound familiar? This is where we introduce the stack to our computer. Instead of reserving a register for saving the return address, we can reserve a register to act as our stack pointer. And whenever we want to call or return from a subroutine, all we need to do is push or pop the return address from the stack. We will need to add some additional control lines to manage the stack pointer, but if we store the stack in RAM, our computer requires no additional hardware. Now, as the control circuit stands, it's pretty basic. All the computer does is cycle through this massive table of control bits, and programming it requires intentionally setting each bit to achieve the desired behavior. This does work, but it can be a real pain, especially if you have a lot of control bits. One alternative, though, is to use a lookup table to store commonly used instructions. The result is, instead of your program containing these instructions, it would contain a reference to these instructions, commonly referred to as opcodes. That's not the only improvement we can make, though. The instructions I provided here are enough to perform the basics, but if you play around with these ideas long enough, you may find that some sequences of instructions tend to repeat themselves, like swapping registers or saving groups of registers to memory. In those situations, the ability to create new instructions that are actually compositions of other instructions can be useful. In order to achieve this, the computer needs to be able to execute multiple instructions before incrementing the counter register. This sort of complex control flow is the perfect environment for a state machine. Creating a state machine that produces sequences of control signals before giving the signal to increment the counter register is actually a lot easier than you would expect. In fact, loads of new possibilities open up if you use a state machine. If you have a latency issue with RAM, you can have the computer wait for the ready signal before completing a memory read or write instruction. If you want your computer to wait for the user input, or better still, drop everything and respond to the user input immediately, you can use a state machine to bake that sort of behavior into its execution cycle. That's not something I'll be covering in this video, but I'd still recommend playing with the idea. Speaking of playing with ideas, if you want to build a computer of your own, but you're not sure what instructions to include, you can use other CPU architectures as inspiration. And if you want a technical description of what those CPUs do, well then you'll want to look up what instructions the CPU can execute. This collection of instructions is referred to as an instruction set, and if you just Google any CPU followed by the words instruction set, you'll get a lot of good information that will help you get started. And that's basically all you need to know. With that, you have everything you need to be able to design and build your own computer. Now, I know I glossed over a lot of the major details and certainly didn't show you how to build anything in any particular medium, but that was the point of this video. I didn't want to show you how to build anything specific. I just wanted to give you sort of the gist of what it takes to build really any sort of computer. The rest is to be left up to you to decide what kind of functions you want to use, how many registers, what the architecture is going to look like. Feel free to just play with the idea, place components together how you think it'll work, and see what works and what doesn't work. And if you believe that the journey ends here, believe me, there is still so much more that we can cover. I mean, we just scratched the surface of just a basic general-purpose computer, but there are other architectures that we can cover, such as pipelined architectures, out-of-order operation. There's really a whole host of subjects that we can cover that I just don't have time to get into at this point in time. But even if I don't cover those subjects myself, all of this stuff will still give you a good starting foundation to be able to study those things yourself. I'd like to take a moment now to thank my patrons over on Patreon who have chosen to support my channel and bring tutorials like this to you. If you'd like to support my channel as well, feel free to check out my Patreon, the link will be in the description. Members of my Patreon get access to exclusive content, voting power, shoutouts, and in the near future, exclusive tutorials available for members only. Again, if you'd like to check out my Patreon, the link will be in the description. I greatly appreciate your consideration, and thank you for your support.